Okay, so welcome back from your spring break. I think you have received your grades. I think I'd asked them to publish them just before coming into this class. Did you check your grade that you got? Yes, okay. So I also provided some thing I asked you, how did you find the midterm? And was it fair or it was difficult? And most of you responded it was difficult. Okay. But I also heard that it was too long. Too long. Somehow it was a lot of computations, something like that I heard. Anyway, we cannot really change the past, but we can always look forward for the final, yes. What we will, I will start today. This is basically obviously the beginning of the second part of this exciting course. I'm going to start with a project presentation. Your project is going to be due, if my memory is correct, May 3rd. And actually, I forgot to put on my mask. So May 3rd is going to be your, so you have something like a month to complete it. Okay. You are free to choose a partner. Just like in real life, choose partners very wisely. There's a lot of partnership issues that I have heard of over the years. One classic pattern is that one partner is doing the work and the other partner is observing the other partner doing the work. If you are in this situation in week one, it will not improve, and you make the mistake to wait, it will not improve in week 2, 3, 4, and so on, and then it will be a disaster. Typically, it is a disaster for both partners. So it is in your best interest to break out of this partnership ASAP. Okay. You don't need to tell me anything of what went wrong. Just start doing the project yourself. If you have contributed and the partner decides on week 4 to clone the whole thing, and somehow because they own the repository lock you out, then I need to know. Okay. So make sure if you decide to partner that you have commits going into the repository so you can prove your contributions. Okay. So 2 people maximum per project. Obviously, if you decide to do on your own, that's not going to be a problem. So over here, we are trying to see how 11 Labs is doing the dubbing service. Anyone is using 11 Labs right now? Okay, 1 person, okay, 2. All right, so they are sort of a well-known kind of shop for speech and audio. What is video dubbing? Probably you went through the project specification. Your end deliverable is, of course, what it is explained in this video. But in a nutshell, you are going to be producing a video that is going to be in a foreigner language. The translation and the audio in that foreigner language, both in the foreigner language, needs to be synced, aligned, if you like. And so that is not an easy problem. So the project is a bit challenging, and the reason why projects are challenging in this class, because it is very simple. The projects are supposed to help you find a job, supposedly. But condition on everything else that is going on, I think that if you do this project, you will have at least some claim that you have done something non-trivial. And that's the whole idea. The project was given to students 2 years ago, I think, in this class, and the outcome was not very successful. So this is my second attempt to sort of try again to see if this time it will be a bit more successful. I sat down and I did, perhaps spent too much time on it, but anyway, I sat down and I did an app. It's a Fast API app. Fast API is a REST API kind of server, well known for its asynchronous capabilities, and routinely used in many generative AI applications. In fact, there is a book in your library, O'Reilly library, called Fast API for Generative AI Applications, if you want to see a little bit more about that kind of topic. Nevertheless, there is an orchestrator who is based on Fast API, who is orchestrating these kind of stages. The download stage, the transcription service, which is based on Faster Whisper. The translation service, which is translating from, in our case, you can select whatever language you can or you want, condition on the fact that the services are able to support the language, of course. And in this case, we're using Spanish. And of course, the Spanish text needs to be spoken, and therefore it needs to spread. Each service is actually there. And then stitching together the video, the original video, together with the captions, the translated captions, and the audio, are going to produce at the end the final deliverable. The problem, as you probably have heard or read from the project specification, is that the time that a spoken sentence in English is allotted, right, in the video, and the time that this same Spanish sentence, let's say, is going to be needs to be translated to say exactly, to convey exactly the same meaning, are not the same. So if Spanish, let's say, typically take longer, right, to say the same thing, then obviously you need to solve what is called the alignment problem then. Okay. So solving the alignment problem is why we have this project, mainly. As I said, right now, at least, you will have a Docker Compose file that you will be able to launch. We are trying to provide both NVIDIA and CPU sort of capabilities in the Docker Compose. So who has already launched the Docker Compose? One person in an NVIDIA? In NVIDIA or CPU? NVIDIA, okay. All right, so there are some containers that are doing the heavy processing here. Because it is a batch system in a sense that, yes, you are going to be processing, but it's not something kind of real time. It's like inference type of processing. I'm not expecting any significant issues in terms of compute here. But nevertheless, in my environment, I had capabilities to run on GPU, so I cannot run it on the text to speech and the speech to text. Out of the many videos I'm giving you, one video in particular is shorter than the others. And if I remember right, it is the very first video. They're all 60 minutes videos. Well, if you open the website now, the app, the Strait of Hormuz video is at the top. So that's the shortest of the two. Having said that, you're free to chop that video into, let's say, 5 minutes, whatever the time is, and experiment with just a 5-minute video. Okay? Because experimentation needs to have multiple iterations. You are not going to wait for the whole video to be transcribed, and so on. Now, that is not in the critical path so much because, as I said, there is going to be, when you run the pipeline, you will see pipeline data directory being formed in your local environment. And inside this pipeline directory, there's going to be plenty of data files, or files that are being created. These files correspond to a specific configuration out of this 3 tasks or subtasks which are explained in other kind of notebooks. One is the alignment method. The name has changed since I posted this image. Alignment method. The diarization, which is basically, okay, there's an interview. Obviously, there are 2 people in the interview, let's say. In some videos, there are more than 2. So obviously, if a man speaks, the voice cannot be that of a woman. And therefore, the idealization is to understand who is speaking and therefore call another use another file in that has the speech attributes from in the speech to text to speech stage. And then voice cloning, you're trying to make the spoken Spanish, let's say, language with the same attributes as the original speaker. So a lot of stuff are actually happening here because of the multiple choices that you could select. It's very difficult to see here on this kind of projector, but there is a configuration hash that is being created. So in the pipeline data directory, you will have a configuration hash that signifies exactly what choices you had in the configuration of the pipeline. And under that configuration hash, you will have transcriptions, speech to text, derealizations, whatever. All of the files which the pipeline generates going to be under that specific configuration ID. So I do suggest that you start it ASAP, in fact, this weekend. So decide whether to partner or not. Start it this weekend and ask questions if the description is not adequate, which is kind of very doubtful. But in any case, ask questions. You can ask questions in the thread, preferably in the public domain, so that many people benefit from your answers. And let us know also your experience in terms of bringing up the application. Should be straightforward. Only when you are successful on this video, the Strait of Hormuz video, only then you can submit the others. Okay. Only then, at the very end. You have, let's say, 1 to 2 days to have that kind of process. That's it. I mean, I'm not suggesting that 1 to 2 days is going to be the processing time. I'm just saying that just before you submit it, just run the videos and publish them in your, you can publish them in, where can you publish them now? You can link them in the G drive. You don't want to put it in YouTube, obviously. You can link them in the G drive and obviously share it with NYU and then put the URLs in your README file so that the TAs will be able to listen to the outputs and make a judgment call. There will be no time for any postponement of the deadline. Obviously, the reason is that the finals are starting. Your final is when? May 8th? Something like that, like it's a Friday, May 8th. And you are going to, yeah, if I remember right. And then we need to just finish the grading of the project very quickly. And then we have typically 48 hours to publish your letter grade. Okay. So there is no time for giving you more, to postpone the deadline, anything like that. Wrap up. That's all great. Okay, any questions on the project? I'm sure you have some questions, but start it and see how that goes. I hope you get something out of it. Now, to make things worse, there is going to be an assignment 4. The assignment 4 is going to be most likely published this weekend. And the scope of the assignment 4, likely it will be reduced compared to previous assignments because we want you to focus on the project. And so assignment 4 may be a kind of a light assignment that it will probably take you a few days to respond. The deadline, though, will be for mid-April. So it will give you a full 2 weeks, but I'm just telling you, try to get rid of this assignment 4 ASAP and focus on your project. So today I'm going to move, as I told you last week, whenever we talked, to move to a preparatory kind of step for the natural language processing, which is the discussion on recurrent neural networks and neuro-machine translation. Obviously, neuro-machine translation has something to do with the translation task in your project, although the translation task is not your core request here in that project, or at least you will understand how translations are happening. Now, I'm going to start therefore with RNNs, and I'm going to also emphasize the difference between these guys over here, the hidden Markov models, and recurrency. Recurrency is not, as it was originally advertised, RNNs are dead because we have transformers now in NLP. Recurrency continues to be one of the many tools that are being used in various modeling capabilities that we are introducing or are being introduced in NLP. Then transformers will be introduced as actions that we take in the recurrent architecture to eliminate some of its problems. So we'll understand transformers out of the RNNs effectively and the problems that they were facing in modeling languages with large context sizes. That's basically the plan. All right, so let's get started. Today, we have what, 27? Okay. What is the lecture number today? I forgot. Is it 8? Who knows? Most likely it is 8. Okay. All right. So we will be using in this new family of neural networks, which will be, of course, quite different in terms of architecture than compared to the feed-forward networks we have done up to this moment in time. We have done fully connected feed-forward networks. We have done convolutional feed-forward networks, but we will be using the concept of a state, which I hope you remember from the recursive state estimation discussion. So what is a state, if you remember it? What is the notion of a state? A state is a grouping of potentially many random variables, right? That of themselves are participating in probabilistic dependencies with other random variables, right? But for us, this S of t will continue to be called the state. Okay. And in many systems, the state is going to be affected or observed or unobserved as a solution to a dynamical system, which is in general going to be given by some kind of a function, f of t. Remind you that t, the function could potentially be changing over time. It's not necessarily something which is fixed, but it's going to be the state, as we also saw in RSC, is going to be sort of related to the state previous time, st minus 1, and some kind of action a of t. Some form of this kind of system we saw earlier, called the recursive state estimation or Kalman filter. The recurrent networks that we will see now, however, are completely incapable of modeling something like that. So we will be assuming for the rest of this discussion that this f of t is a function that has absolutely no time dependence. So we are going, in other words, be concerned with, I'm using exactly the same letters, right? I hope you remember, this is basically action, and this is obviously a state, and this is a function that for RNNs will not depend on time. So functions that are giving us this type of relationship, in the case of feed-forward networks, we have not seen. In feed-forward networks, we're having some actions. Actions could be, as I said before, implicit or explicit. For example, action could be the arrival of a new X, of a new data, of a new token, of a new image, or whatever that is. But we never had that. We never had the incorporation of what hidden state we had earlier into determining the new state. So if you remember the trivial element that we had in feed-forward networks, this was the sigmoidal neuron. I hope you remember it. it's kind of trivial now. This is W transpose X, and this is X, this is W. So we had also some bias addition here. So if I start with this, I want to describe the recurrency as an evolution of this feed-forward architecture. I'm going to start with that, and at the end of the day, I'm going to reach a point where that final destination, final block diagram, will have some elements of this equation. We'll implement this equation, again, without the t-dependence. So this is how I'm going to do it. I am going to maintain the dot product. But now, in the dot product, I'm explicitly going to be modeling that data are going to be arriving one after another. Just like in language, as I'm speaking, one word is uttered one after another. Images in video, for example, one frame is arriving one after another. So there will be an explicit, just like we had it earlier in RC, time dependency on the sequence. Okay. Any questions on that? And I think this is pretty straightforward. That's the change that we are introducing here in terms of X. I'm not going to be using the W because I'm going to reserve the W for something else. So instead of W, I'm going to be using U, okay, as the parameter vector. I'm going to maintain the bias. And I am going to replace the sigmoid with tan H, hyperbolic tan function, for reasons which I will explain. And then I will be denoting the output of the nonlinearity with H of t, or something which I'll associate with the hidden state. That's why I'm using H as the hidden state. And how do I model this guy over here? So instead of S of t, I will be using sometimes S of t, sometimes H of t. I need an HT minus 1 here, because my action is the arrival of the new token, for example, or the new frame or whatever. And therefore, I need something to give me HT minus 1. And that something is going to be, obviously, the output of a memory cell. So I need to store. In the previous instance where HT minus 1 was coming in, I'm storing HT minus 1. And I'm now going to retrieve it out of the memory to use it, to implement the equation. So I am going to suggest that the block diagram is going to involve, I'm using capital D because in electrical engineering, these memories are coming in with, are implemented with D flip-flops. Okay, this is like a memory cell, therefore. So let me write it down. And then I had stored HT minus 1 in the memory. I'm retrieving it, and I'm adding it over here. So if I write the forward pass equation of this thing, which I will call from now on the simple recurrent neuron, because that's the sigmoidal neuron, that's a recurrent neuron. But I'll call it simple because it's also a more complicated version of it. I am going to write very easily HT is equal to tan H U transpose XT plus I'm going to introduce here, let me just delete this line. I'm going to introduce here let me move this guy here, HT minus 1. I'm going to introduce a multiplier with W as a multiplication kind of term. So it's W HT minus 1 plus B. So you can see that the function is now that function, hyperbolic tan function. The hidden state is formed by something like this, right? And obviously, it's going to be a dependency on what is really coming in, h of t, x of t. Which of course now brings up, and if I may ask you, what are the trainable parameters here? The theta is going to be obviously u, v, and w. Is w a scalar or a vector? Scalar, because obviously this is scalar, this is scalar, this is scalar, therefore this is scalar. Everything is scalar after this dot product. Which of course means that the hidden state is a scalar. That's the important thing to recognize. Hidden state is a scalar, and the other thing that we want to kind of make sure that we all understand is that this shape of this kind of tan h, the tan h function is going something like this. Okay, so this is the 0, this is +1, and this is -1. Instead of having the sigmoid that goes from 0 to 1, we go from -1 to +1. And the reason why we're actually doing that is that in this kind of feedback loop, that certain things will happen. We do not want to have many zero possibilities. So, for obvious reasons, we prefer to have a function that will give us either positives or negatives. So that's going to be the form of a neuron, and we'll follow a similar trajectory after we see a use case on what is the usage of this type of recurrent neurons, why we kind of insist that this could be behaving better for certain use cases. We'll see a use case right now where it will just use just a single neuron, and then we will recognize some limitations out of that discussion and start putting together many of these neurons together to form layers, to form a recurrent layer. All right, so what is the use case? What is an application? So this is a problem. The problem statement. So we are asked to predict the price X of a commodity in the next trading day using a sequence of capital T is equal to 50 prior prices. That's the problem. It's a commodity pricing prediction problem. Price is a scalar. Because price is scalar, I have hope that this thing will be able to predict a price. Now, the problem, in other words, a bit more graphically, is the following. I have some kind of a T over here. I have X is going to be my price that I'm trying to predict. And someone is giving me some, sequence of prices. And right now, this is 0, this is 49, and it's asking me to predict the X50. We are still in the supervised, in fact, we will never deviate from this supervising in this class. We are still in the supervised kind of business. So obviously, they will give us the ground truth. And they ask us to use something that will allow, after training, for this prediction to be accurate. No surprises in terms of the setting. The environment is against stochastic gradient descent. The losses are obviously what? What is the loss for this problem? Mean square error, because it is a regression problem. It's a regression, it's a price prediction problem. And what we will do is we will then perhaps I can go to your notebook if I'm lucky enough and I have it here. Okay. It seems that I need to launch the application. I don't have the notebook right now. Hopefully, this application is going to be in the same state as the notebook I had in the site, and somehow it was not linked. I'll fix that tomorrow. But the discussion here in this your textbook is this chapter 13, so that you know. Chapter 13, processing sequences, RNNs, and CNNs. And if I go here, this guy, forecasting with a simple RNN. Yeah, they changed the notebook on this release. So I want to go to the second edition and not the final, the third edition. Hold on a second, John. Yeah, I want to have the third edition because I want to refer to this notebook that I had also. The reason actually I'm referring to this notebook is the data set is synthetic, and because the data set is synthetic, I can make certain extrapolations from the data that I cannot do with non-synthetic data. So that's why it is a bit okay. Okay, so this is chapter 15. Is yeah, forecasting using a simple RNN. That's the notebook I'm looking at. Okay, so this is the data. Oh, did I hold on a second. It's actually the second edition that I'm. Anyway, I will draw it, so I don't need to go looking. So the reason actually I wanted to show you this synthetic kind of data is I wanted to ask you a question. If someone is giving you a problem with something like that and is asking you to build a predictor, the question I have for you is, can you solve it with this data? What would you do? How would you train a network, right? In this case, it's just a single neuron, to do the prediction? Any ideas? Because the recurrency, I mean, will work as follows. You will feed x0 in, then, well, you can start with some kind of initial kind of hidden state. You will feed the first data point in. You will get the H1, right? You will then the H1 will become H2 when you feed the second point, and so on and so on. And then finally, you will have an H49 that will give you the last hidden state. So the last hidden state is your prediction of the price of the commodity that you were after. The question I have for you, though, is how many sequences have you observed? And the answer is obviously you observed only one sequence. And I want you to then make the relationship between this and, let's say, a computer vision data set. If someone is asking you to do, let's say, build a classifier, or even in the object detection regression of the location of the bounding boxes, right? If you remember, how many data have you received? Were you received? You were given probably hundreds or thousands of images. So one conclusion we can actually make is that typically out of one sequence, we cannot train anything. Because someone will say, hold on a second, but if we can create some kind of a situation where we present some form of a sliding window, right? Where we are making predictions, and this is one sequence, this another sequence, another sequence, another sequence. So we can generate out of one sequence many kind of sequences. The problem there is that obviously you cannot cheat that way because all of these sequences will have pretty high correlations with one with another. So correlated data, if you remember some discussions we had in the past, does not really help your prediction. So the answer to this type of problem someone will give you is just you need to give us more sequences. We need to observe more than one sequence. In fact, in the notebook, which I was not able to bring up, there were 70,000, if I remember right, sequences, or something like 10,000 sequences. And then we break it down into 7,000 sequences for the training and 3,000, let's say, sequences for the test data set in order to be able to, for the stochastic gradient descent, to have enough iterations in order for it to be able to converge into anything. So well, the outcome of this kind of discussion is that we need more than one potentially thousands to train the predictor. For each sequence, we're going to get a y hat. For each sequence, we're going to get a y hat. With 10,000 sequences, we're going to have 10,000 y hats. Within this period of time of 10,000 y hats, we'll be able to converge in terms of mean square error to some theta star, I called it earlier. And with that theta star, we can actually do now inference to see exactly if the predictor works fine or not. And someone did that in that notebook and produced, if you like, a mean square error, fine, because now we are able to generate many of these kind of sequences and train this kind of thing, and found a mean square error of this predictor. But someone actually said, okay, hold on a second, why do we need this thing? Can I just take the whole sequence in and use a dense approach, right? In order for me to predict, instead of the sigmoid now, have just a pure linear kind of regressor to predict the price. And if you do the second one, you will find a mean square error for the sort of a dense kind of sort of a predictor is going to be better than this one. So why we do that? But we are comparing apples and oranges there in the sense that the dense predictor has how many parameters? Has 50 parameters plus the bias term 51. And here we have only 3. We only have 3. Because x's are scalars. Okay, so the second kind of observation is that this, we're not supposed to, for the same number of parameters, we have to increase the number of parameters here as we have done kind of earlier in order to compare. That's point number one. The second point is that, so let me write this down. So price prediction may require larger number of parameters. Than 3 that we have here. See the theta vector. So if we are to increase the number of parameters, then as we have done in the conversion from a single sigmoidal neuron to a dense kind of layer, how we call it, how we can go about doing that? That's the second kind of question. And obviously, we can do that by That's point number one, increase the number of parameters. Point number two, if we increase the number of parameters, just like the sigmoidal neuron became now something that involved the matrix by vector multiplication plus bias. Now the bias was a vector, resulted into a hidden state or a hidden latent variable, which is also a vector. If we do the same thing here, obviously the latent variable here will be a vector. Because that's the only way we can increase the number of parameters, to increase the whole dimensionality of the whole recurrent circuit that we actually see here. So if this h of t becomes a vector, how can we predict price? Because the hidden state will then be a vector. So how do we go to price? So we have to do two things at the same time. Increase the number of parameters to be able to match potentially plain old simple linear regressor. And the second thing we need to do is to decouple the hidden state from the predicted state, from the predicted variable, from the y hat. This h of t cannot be now the y hat. It has to be something different. So let me write down number two. The thing that we need to do is to decouple the hidden state h of t, which is now a vector, from the dimensionality of the target variable. So we arrive gradually in what we call the simple RNN layer now, that will consist of multiple simple RNN neurons. And the layer is going to, as a block diagram, will look like this. We're going to have similar constructs like a matrix. The matrix will multiply now a vector. The vector will be the concatenation of two things. First, the x of t, as it was before, and also the ht minus 1, which is now a vector. There will be a bias, a vector now, and it will be a tan h. So remember, tan h is when it's a vector in vector output are applied element-wise. This will be now my vector h of t. This will go into the memory, and then the memory is going to the vector stored in that memory is going to be retrieved in order to implement the forward pass from previous iteration. So this is the block, kind of a block diagram, but in terms of an equation, I would like to split it up into two steps. So h of t is going to be tan h of, there's going to be a matrix U that is going to be n input by n neurons, x of t, which is obviously n input by 1, plus W prime. I will tell you what the W prime matrix is, which is n neurons by n neurons times h t minus 1 plus b. And if you compare this equation to what we had before in the single kind of neuron equation, you will see the analogies. The U became now a matrix, and the scalar W became another matrix called W prime, which I will define. The main parameter here, obviously the n input we knew right from before. The main parameter here is how many neurons we have in this layer, n neurons. So which means that the output is going to be n neurons by 1. Okay, so what is now the W matrix I have in the block diagram? The W matrix is going to be U transpose, W prime transpose, which is going to effectively result into, if you do this, in terms of dimensions, it will be n input plus n neurons times n neurons. That will be the result of that. And the forward pass equation, which is exactly what the block diagram kind of indicates, is that can also be written then as tan H of the concatenation of xt ht minus 1 vectors W plus B. So this is the final kind of equation that is giving us the simple RNN neuron. It has n recurrent neurons inside it. If you compare that against what we have seen kind of earlier, H was ReLU of what? Wx plus B. You can see the close analogies between one and the other, except from the fact now, obviously, that we have the previous hidden state coming. So the green is the feed-forward dense layer. This is the recurrent layer, simple RNN recurrent layer. Also we call fully connected dense layer. Okay. Which of course brings us now to the following last kind of point. We did the increase in the number of parameters. We increased the number of parameters of this thing. Now this thing is giving us the vector H. There are two questions at least should be in your mind. The first one, how on earth did we potentially, is there any intuition to how many neurons we need for the problem that we were facing with the stock price prediction problem, the commodity prediction problem? And the second is we still haven't done the decoupling. We still have a vector, and somehow we need to take that vector and make it a scalar, because that's going to be our y hat in this case. So the first question is a bit more interesting that perhaps it allows you to think. Any ideas how we should think about determining this n neurons for this price prediction problem? Remember, you're given potentially thousands of these sequences with the request. The request was the next trading day, ground truth. And you are coming up with some dimensioning kind of exercise for this simple RNN kind of layer. What say you? What do you think how we should think about this problem? I mean, one way to think about this problem, and it could be many, but one way that I think a little bit about this problem is that the answer to the question, how many factors you expect to affect the price of a commodity? I mean, the intuition says that the price of a commodity will be affected by macroeconomic factors in terms of competition in that kind of market, and so on and so on. So definitely what we are after effectively is some dimensioning of n neurons that it will capture the answer to that question. How many potential factors we expect to see there? Because out of these many factors, whatever my h of t vector is, that is basically what it will represent. If the h of t representation is the right one, that vector, if I attach it to something which I will call it the head of the simple RNN layer, I will find a good y hat. I will find a good price at the end of the day for that specific thing. So someone could actually suggest the following. Well, I can put all the sequences in one gigantic capital X matrix. All of these columns are trading days. This is the trading day axis. And these are values. I mean, these are basically, this is basically the t-axis, right? And this is I'm giving you M sequences, right? How many of these do we need? This X matrix captures some form of what? Now, temporal correlation. Can capture some form of temporal correlation if you form the covariance matrix out of this guy. I can take X and I can transpose it, I can multiply it with X to come up with a 50 by 50 covariance matrix. Can I do that? Because this guy is 50 and this guy is in the 10,000s, right? Let's assume this is 10K, right? So if I do X, the X is now 10K by 50. And I do now, so therefore I will transpose it, this guy, to be 50 by 10K, and I multiply it with another X, right? And therefore I'm obtaining something that it is 50 by 50. What do you think this 50 by 50 tells us? That it tells us, it's telling us a story. What story does it tell us? Do you expect intuitively that the price of a stock will be highly correlated between successive trading days and not so correlated between trading day 1 and trading day 50? Is this a good intuition? It is a good intuition. So that matrix is capturing, in other words, some structure that we see in that commodity. I mean, if that commodity is oil, then there's going to be, because there's a cartel for oil, so there's going to be obviously a lot of strong correlations between trading day 1 and trading day 10, minus geopolitical effects, right? There will be almost like a flat line kind of thing, right, over 50 days. Obviously, there will be fluctuations with larger kind of time durations, but at the end of the day, I'm claiming that if someone takes a PCA out of this C, the principal component analysis, right, thus takes the SVD of that kind of C, it will produce some kind of spectrum of latent factors that are affecting the price of the commodity. That spectrum of latent factors, if you think about it, if you rank them, is most likely going to look like this. Some factors are going to be really important for the commodity. Some other factors are not so important. Just like you do in PCA, I can chop off some of the factors which are not important and keep only the ones which carry the biggest impact. And I'm claiming that this exercise that I just did is a good guidance to select the N neurons, because the N neurons are going to pack into that H of T vector the important factors. If your H of T vector is too long, too large, right, as a tensor, it will bring quite a lot of noise into the prediction. If it is too small, right, it is a compact kind of vector, it will leave important information out. And so that's a good design approach to think about that intuitively, how much neurons we need to invest in that kind of predictor we are building. Which of course brings us now to the last point. How do we get the y hat as a scalar? And so simply, based on everything we have done in this kind of course, someone suggests that I'm going to take my H of T, which is a neuron by 1, by the way, and I'm going to pass it through a V matrix. I'm going to add to it a C vector, which is the bias term, and I'm going to come up with an O of t. It's not a 0, it's an O output. And this O of t vector, if it is a vector, I can actually can support many downstream tasks. Right now I have a prediction, a task for a scalar, right? So I could have done it in a one shot, but I can still support the regression task by having a kind of a second stage where the E vector is going to result into my Y hat of t. That is the kind of regression, the regression kind of branch. But I may have use cases where I have a classification. Well, in this case, there is a very simple language model that can be constructed. Someone is asking me, what is the next token as a prediction? Well, the token is a discrete thing, right? So I have to choose the token out of a family of, let's say, 10,000 tokens. That's a classification downstream task. So I will face both of these tasks. So I will obviously take the softmax in this case, and therefore form my desired Y hat t, which is now a discrete posterior probability distribution. So I haven't really done anything intelligent here. I just did dimensionality matching. I took whatever neurons they're giving me, and I resulted into a scalar here, and I resulted into something which could be smaller or larger than n neurons. Depends on the dimensionality of the V. The V, don't look at it this way only as a projection. Look at it also as a lifting matrix. A matrix that lifts dimensions. In other words, it takes n neurons, which would be 100, and produces something which is 10,000, because this posterior probability distribution has to be over all possible discrete classes that I need to support. And as we'll see, in natural language processing, the number of classes are pretty large. So both of these tasks are supported by this. And that's basically what is going to be the head of the network overall. I have just one layer and a head. But I can have more than one layer, just like I had it earlier, and therefore I'll arrive in a very similar architecture as we have seen already, which I'm not going to repeat. I may have a concatenation of this but I'll show you a block diagram now. So this kind of block diagram is kind of pretty straightforward. I have the X of T's coming in, one at a time. I'm forming a hidden state, and I'm feeding into the head. So let me plot this thing as instances now, multiple instances in time, because I want to eliminate really the feedback path. I want to go into an architecture where this feedback path is kind of confusing. So I want to still treat it as a feed-forward network. And that's the block diagram I want to draw right now. I will explain this block diagram when the feedback path is eliminated. This does not mean that I don't have memory, but I will create what is called an unrolled virtual architecture of an RNN, where we will present what's happening over multiple instances in time. So right now, physically, this is basically the block diagram. But if you unroll it, you will see what happens in H1 when you produce H1, what happens when you produce H2, H3, H50. So I'm going to have effectively 50 of these things, one after another. I'll rotate the whole thing kind of 90 degrees, and I'll plot something which will answer some questions also about memory. Okay, so this is a question I want to answer in this block diagram. Can simple RNNs capture long-term time dependencies. I mean, that's a question which affects the problem we already have seen, because you told me that if the commodity is a stock, then the time series plot over here exhibited quite a lot of significant fluctuations from one trading day to another. So it's not evident why we need, first of all, long-term dependencies. But if I give you another application, a commodity that does not really have this type of rapid fluctuations, or language, where in many instances, in order to understand the meaning of something, we have to go forward in the text a couple of sentences. In this kind of applications, we may need to capture long-term dependencies. In other words, we are after temporal patterns that last quite a long time. So this temporal, we were looking at spatial correlations in the CNNs. Now we are looking for temporal correlations in the RNNs. And these temporal correlations may span long periods of long sequences. We need to be able to see how the, let's say, price over here could affect the price over there, or the mention of a token here could affect the meaning of a token over there, just to use both of these applications in one graph. Okay, so I'm going to do that. I'm going to just draw just two instances in terms of what happens in the RNN, and to be able to answer this question. And I'm going to use some basic backpropagation intuition to persuade you that there is a slight problem with this architecture. So I'm going to have one detailed column, and the other will be not so detailed. So I have a computational graph that looks like this. I'm going back to the equation where I was using U and W prime. Okay, so this is H t minus 2. This is U x t minus 1. These two were added together, and together with a bias term, B, was giving me some form of an activation vector, AT minus 1, was passing through tan H, was forming the HT minus 1 hidden state. Okay, and then the HT minus 1 was going through the matrix V, going through the bias C, and I'm going to just do the classification use case for a change. This one will give me the y hat of t minus 1, and then over here I'm going to have a cross entropy with the y t minus 1 as the ground truth, and then I'm going to get a loss L t minus 1. For those who are wonder what on earth is this thing, is the whole thing that we were discussing with the head now. And this column is everything that happens when xt minus 1 is coming in. When xt minus 1 is coming in, I already have an ht minus 2 coming in too. And then I'm producing an lt minus 1. In the next instance, there will be another column next to it, because now I don't have any feedback path now. I've converted the feedback loop into a feed-forward architecture. So I have, I'm not going to draw everything, of course, but I'm going to have over here LT, I'm not going to draw anything. Everything is common here. But I want to emphasize the latter part over here. Okay, this is common. At the input over here is HT. I have tan H. And over here I have H T minus 1. I have XT. Okay. This is a second column. Is when XT is coming in. XT is coming in. Ultimately, I'm getting a loss. Now you're going to say, hold on a second. Why are you calculating losses for this problem? Because this use case may require it. There are use cases like when you try to detect sort of some kind of in a sentence, whether it's a toxic sentence or not, right? You are not claiming that you are going to do the classification to toxicity or not, right? When you see the first token, the first word, but you have to wait until the whole sentence is processed, right? Like a whole sequence, right, of tokens, until you say, okay, this is not good, or this is okay. If you developing a filter such as this in an NLP application. But in some other applications, we need to predict all the time. Okay. For example, in a generator, in a language model, we have to predict the next token all the time. We don't stop. So depends on the application, the head will be active or inactive, right? But no matter what, you're going to have a head at the very end. For example, if you are talking about a sort of toxic tweet classification, or whatever you want to call that kind of application. So what I have drawn here is, if you are processing a sequence of, let's say, 50, you're going to have 50 of these guys, one next to another. They are, however, connected. Where is the connection? The two columns are connected with each other. Where is the connection? Which one? HT minus 1. Yeah. So there's an HT minus 1 here. This line causes significant effects on the training of these networks. Remember, in this representation, we have no feedback loop. We have 50 of these guys all the way until the wall and beyond. So when you look at the backpropagation, you're going to start potential at the end. You're going to have a gradient flow going. Remember, in the backpropagation, we were going from this guy, goes through all the stages over here, which I didn't draw. You have a gradient here for this loss with respect to this tensor, right? Goes through the nonlinearity, splits up into goes over here. The same thing happens over here as well. Look what's happening over here. The flow, the gradient flow goes here. Remember this junction gates that I told you to pay attention to? What happens to the junction gate? Addition. That is the important thing. There's addition between the flow from here and the flow from there. So if I have an application where the losses are calculated every time, right? I'm getting some assistance from the presence of the gradient that goes through here, right? So I'm get some kind of amplification of the gradient over here, and I'm going to go back, and I'm going to do exactly the same, and I'm going to go back. I have to go back 50 stages to reach H1. When I reach H1, that's the end of upper propagation. Every time that I'm back propagating, I'm giving opportunity to these tensors to change. If the gradient flow is pretty small, however, this tensor on H1 stage, on the first stage, will not be changing. As the network becomes longer and longer, the sequences are becoming longer and longer, right? The gradient will actually typically either will blow up or it will diminish. And who is the main determinant for the diminishing or blowing up of the gradient? As it turns out, it is this guy. Because it is that matrix and the eigenvalues of this matrix that will determine what will happen to the gradient. In fact, it is really this gate that, because, and the main determinant here is this matrix that will determine what flow it will go reach this line. And if it reaches this line, it will reach this line, some version of it will reach this line that I have not drawn, and so on, all the way until H1. So the memory that we say in general is the gradient flow. How much of that can I remember? In other words, can I propagate in order to be able to change what I have seen here in this time instance, to be able to change what another price or another token, which is affected by this token, for example, here. So this is the relation. This is the span of temporal correlation which I can, or patterns which I can detect. If the gradient is not performing well, if it is diminishing, then my memory is not going to be that good. So this is the main reason why we moved away from this type of architectures, the so-called simple RNN architectures, to the so-called more complicated RNN architecture called long short-term memory or LSTMs. This is the reason. Now, if you want to deep dive a little bit further into this, in Ian Goodfellas' book, there is quite a lot of discussion on this specific diagram. And the backpropagation equations are there as well. But I don't advise you necessarily to know anything about it during the final or any exam. I'm not going to ask you that. I'm just presenting what is really happening, so you at least have some justification in your mind why LSTMs came to be as an architecture. Okay, so we are now going to be drawing a LSTM architecture, and we will recognize also, although we're not going to show it, that even that architecture may not necessarily be solve the main problem. Okay, it will solve it to some degree because we introduce some additional capability. We'll introduce a capability that we borrow from ResNets called highway paths in the gradient that are, backpropagating nicely. But obviously, we cannot really do miracles, and that's the reason why when we break the recurrency in transformers, the issues that we see here are not happening, or at least are not happening the same way as it's happening here. All right, so what I wanted to do now to just plot over here the long. This is very interesting. I'm going to take it to the store. long short-term memory or LSTM. So this architecture is going to be a little bit involved. Maybe at some point I should switch to slides and click. That's easier for me. But anyway, I'll draw it. It's okay. Okay, let's see. Let's see if I can manage to draw it as good as I have in paper. So we have input dense layer, which accepts xt minus 1 and ht minus 2. I'm going to draw two stages again. I am going now to introduce what we call here as gates, and this is the first gate, input gate, that accepts again ht minus 2 and xt minus 1. There's going to be, maybe I can do it here. Another gate called forget gate. This is a summation from the second, let me call this a long-term state, st minus 2. Everything is a vector here, of course. This is not a sum. It's just a junction. This is the tan H. And this is the output gate. And this cell, I will call it cell, this cell is the LSTM cell that is going to be repeated so it will fit at ht minus 1, and this is st minus 1. So the same cell is going to show up over here, exactly the same. So two things are happening here, which is different from the simple RNN. Probably you recognize some elements of the simple RNN. You recognize the tan H, obviously. You recognize the fact that I'm having a layer, the input test layer, which is doing this u h of x of t plus ht minus 2, right? The w ht minus 2. This is actually happening here. But there are some new things as well, like the presence of the gates. And the gates, the way to think about it is the following. This is just pure intuition. Gates are there to preserve the memories because most of this, all of these gates have an output stage, a nonlinearity at the end, which is a sigmoidal. Being sigmoidal, it is between 0 and 1. So whatever vector is coming in, it is adjusted, each element of that with a knob of 0 to 1. So depending on the value of this kind of knob, some memories, some tensors are being either forgotten or let go untouched through the remaining kind of cell. And we have multiple gates. We have certain things to remember about the input, therefore, previous prices, previous tokens that we have seen already, right? If we are in this kind of stage. We have two memories, two states effectively here, two hidden states. The original one, let me call that the short-term hidden state. And a new hidden state, which is the long-term hidden state, S of t minus 1. Mind you that this S of t in general, S t minus 1 here, mind you that it is goes all the way untouched depending on this forget gate. So remind you the ResNets, we have this kind of skip connections. These ResNets and LSTMs are incarnations of what's called highway networks, because we are typically supporting this highway where we are borrowing the long-term memory and we are using it to form the short-term memory. In other words, bring things that we need from the past to form something that we need right now. And depending on, so after we use it, we put it back into the highway for the next stage to use it. ST minus 1 for the next stage to use it. So it's not very clear, the whole block diagram. I'll give you that, but I'm trying to explain as much as I can. The output gate, the input gate, and forget gate are effectively adjusting what we need to remember with respect to our inputs, what we need to remember with respect to the short-term memory, and what we need to remember with respect to long-term. That's basically the role of the gates that are there. So for example, I'll give you an example. Maybe this example will be okay to remember it as an example if someone asks you. This is from an NLP space. Let's say this is an example. Let's say the bank introduced a new savings account. The bank, comma, faced with criticism over interest rates, comma, introduced a new savings account. Okay. If this is the input and the task is summarize the input, a text summarization kind of task, this should be the output. So in this kind of task, in this text summarization task, the LSTM will actually be learning the elements that are needed. Remember, the gates here have trainable parameters. They are not fixed, right? So the sigmoids are trained from the logics which are being formed, right, inside this kind of gates to potentially forget input that are over here. This input will be forgotten. Let's say this is the input, that's with the input gate. We'll learn to forget what I drew here as the green part of the sentence. Let effectively summarize the output and produce this output. It's just one example of trying to put some intuition behind the role of this kind of gates. Yes.
What's the reason for the forget gate? No long time.
The forget gate is only affecting the state, this S of t minus 1. And because this is like a latent kind of thing, right? I cannot really give you an intuition, but this is like, in order for me to form the output, which is a latent and the output is always something which is a head is crossing from these latent variables. I cannot really give you the intuition. However, I will point out one video that tries to explain with animation. The video is on in your site on the LSTM. So this is the architecture I just drew. The video number 4. I want you to click and watch that video. This video is has a use case of what are we going to eat tomorrow, given, which is a problem that everyone is facing, given that what we ate the 4 previous days. And with animation, he is explaining in a very intuitive way what's really happening with respect to the short-term and long-term memory. And I think it's a pretty good video. I cannot do animations, but he has pretty good video for you to put your head around LSTMs. I'm typically not bothering you in final exams with LSTM questions because of it takes a while to explain everything. But if you understood the intuition behind the simple RNN and the reasons why we kind of want to introduce LSTMs, because of the highway connection, if you like, where they solve some of the problems of backpropagation and the gradient field, that is plenty. That is basically what I want. But if I were you, I would just spend 15 minutes watching that video. Maybe something else will click that I am not able to convey right now. Yes.
So is the reason why we added that long?
This is the reason. This is the reason where the S of t, which is almost unobstructed by other gates, except from the forget gate. This is the reason why the gradient survives longer in LSTMs as compared to
the same thing as the resonant, where it's like a short.
Same thing as LSTM. They are called highway network architectures for this reason, because this is the highway, that line.
Okay.
Yes.
Yeah. Does ST-1 also have the knowledge of ST-2? Because the lines are continuous.
Sorry, can you repeat?
So if you go from forget gate, there's a line that goes to ST-1. So does ST-2 is also accessible at the end?
So yeah, so the ST-2 is after the forget gate. Let me just make sure that I have the format diagram in the website. Hold on a second. Do you see that here? Where is the forget gate? Forget gate is the blue one, right? So you have to rotate it a little bit in your mind, right? So the cell state over here, right? So ST-1 is going through the multiplier with the forget gate. And finally, ST is formed at the output of this summation. Do I have it like this over there? I have ST-2. Here I have ST-2 and ST-1. That's what I have, right? So ST-2 is multiplied with the forget gate, right? To form after the summation, and I think that's what I drew. After the summation, ST-1 is formed. Okay, so if you compare this and this, the only difference is the time, the indices. Is that what you're asking?
So the connection between ST-.
So ST-1 is here
Got it.
at the output of the summation. It's just that because of this, I have to show that ST-1 now is part of the long-term memory, right? And that is being propagated forward to the next stage. All right, so if we understood something about the reasoning of LSTMs, the next thing I wanted to do is to suggest how potentially these RNNs and LSTMs could actually implement a task which is associated with natural language processing, like a language model, a simple language model. And the simple language model, in order for me to present a little bit the simple language model, I want to spend some time on introducing the domain of natural language processing and at a high level, and then see if we can actually get to understand, let's say, a character-based simple language model, which is tokens will be characters, and see how we can actually make a prediction there using these RNN architectures. Okay, so with that said, I'm going to just start the NLP discussion. The processing, not modeling. Although modeling is what we do. Okay, so remember, we started this kind of course by giving you some form of an environment where an agent with ego motion was acting in that kind of environment. So over here, we are going to still have the notion of environment, and we're going to have on the left side, draw, if you like, an agent that will do some task, like chatbot type of agent. This is, of course, a block diagram that is sort of evolving as we speak, but this is more conceptual than anything engineering. So we had this notion of a state, and remember that we were getting some raw sensing information in. Well, in our case here, the raw sensing could be text. It could be audio. It could be video. It could be anything. It could be an image again. But let's focus a little bit on the text now rather than the images, because we already have some experience with that. And I want to call the first stage kind of a parsing. And inside this kind of parsing, I will put several tasks that are not necessarily anything formal here. It's just things like segmentation, where someone is taking some kind of a document and chopping it off into segments. Like, for example, a sentence is being segmented into words, let's say, at broad terms. Some form of tokenization, where tokens are being created out of words, and we'll see the tokenizer in a few moments. Maybe tasks like part of speech tagging, also known as POS. And part of speech tagging is a task where I'm going and classifying every single token, let's say in the sentence, as is the verb, is a noun, is a subject, or what it is. Right? I have tasks like dependency parsing. I'll show you in a moment. Named entity recognition. Or any and others, co-reference resolution. So let me show you some examples of that, so we don't just some examples of let's say named entity recognition. But actually, we are going in the text, and we are tagging specifically for tokens, in this case words, that belong to certain categories. In order for us to improve the understanding of the text for any downstream tasks that are to follow, including modeling. So over here, obviously, that's a date. This is incorrectly tagged as an organization. There's another error over here. This is definitely a person, but definitely this is not a geographical entity. as it is, this tag is. You don't know it, but I'm telling you this is geographical entity. This is tagged incorrectly. It thinks that this is a Maryland, the state of Maryland, while this is an MD that's a profession. So that is basically an example of named entity recognition. There are certain libraries which are almost a de facto sort of libraries to use, like Spacy is one of them. NLTK is another one. Historically, NLTK was for academic purposes, and Spacy was for sort of more industrial kind of use cases. It still is the case to some degree. Okay? You can actually see here how straightforward it is to implement a task like this using the library. It's just one line of code. Other tasks that I mentioned include core reference resolution, for example. So you can see that as an example of what we also were discussing a few moments ago, of the need to have long memories, to preserve long memories. When you read the sentences, for you, it's very straightforward to associate it with London. But obviously, we have to achieve the same thing with the machine. So during this kind of stage, we can actually extract certain information out of the text that we will use for any downstream kind of tasks that is to follow. So in a sort of application such as this, after patching, typically, I think the kind of genesis of this kind of block diagram is some kind of a customer support type of chatbot, right? That it is there. Typically, you want to you already have the capability to build some form of knowledge base, or KB as it's actually known, shown over here. And this knowledge base, there are many approaches to build knowledge base, obviously very modern approaches, but outside of how you build it like a knowledge base, treat this as a kind of a database over which you can do things like semantic search. So for example, in a customer support kind of bot, customers are inputting kind of text. Evidently, the state is completely impossible to estimate. It's not an estimation problem of a state here. Because what is the state of a chatbot in a customer service? Well, the state is the state of mind of the customer. The only thing you can do is some form of parsing in order to understand, what, for example, the named entity recognition may point to some kind of product that you have stored some information about in the knowledge base. Right? So, in other words, not everything has to be an LLM of some sort. Right? So there are certain stages that precede, if you like, this generative kind of AI sort of domain. So over here, I will call it the analysis and planning stages. And if I may kind of mention a couple of things here, for example, sentiment analysis may be done at this stage. Is this guy angry of some sort? I mean, it's like, people are saying, all sorts of things. So sentiment analysis. So what is it? Finally, the whole chatbot has some utility, right? What is the utility of chatbot? To minimize the number of times that has to invoke a human operator. So sentiment analysis may be done there. Could be some kind of as I said, some semantic search in the knowledge base in order for the knowledge base to retrieve specific text. Even today, when people are implementing mainly graph-based RAG systems like GraphRag for assisting, if you like, bots such as this, right? They have found that it's much cheaper to retrieve the retrieval task is like a very core capability. I mean, if you screw up on the retrieval task, then the rest of the performance, you can forget about it. That is basically what has been learned out of potentially tens of deployments out there, videos that people have referred to. in this type of systems. So semantic search is still a very, very important capability. And then finally, the chatbot must be able to respond with text. And obviously over here you see the large, in parentheses, language models. Or sequence-to-sequence models. After all, the information could be in English over here, and the chatbot is deployed in a country with not necessarily the same language as the knowledge base is written. So some neural machine translation may be happening over here in that stage as well. So this is like a poor man's kind of chatbot in 3 blocks, right? It's not nothing fancy. It's just it's helping us to understand where exactly language modeling is. The modeling is here at the end. Obviously, the modeling could be in many other places, like inside the planning. Like the language model today is, these language models are involved in this kind of orchestration or planning stages. But definitely the role of the planner here is to, for example, do I have all the information in order for me to send the text? Or do I need to ask further questions, probing questions for this person to respond with more information? Okay. If they tell you, oh, my phone is dead, that's okay, what is the phone? And so there must be some kind of a plan. And these days, when it comes to text, language models are involved in this kind of planning stage. So the borders are not very strict. So the reason actually I wanted to draw this is to tell you a little bit more about tokenization. I'm going to tell you something about language modeling and sequence-to-sequence models. I can't really deal with every single topic over here, but I'm just going to tell you something about these 3. And then for the specific task of having large language model, then I will switch to a new neural architecture called transformers. And I'm going to build transformers, as I said, out of the recurrent neural network kind of problems that we more or less we understood. So I'm going to start with tokenization. So what is a tokenizer? The tokenizer is a device that has the whole purpose of the tokenizer is to give us a vocabulary. Okay, so what will be the vocabulary? Well, a way to think about it is that I will take the sentences that I'm observing, and I'm going to, after some form of normalization or lemmatization, I'll be able to just give you a whole bunch of words as entries in the vocabulary, just like you are using a dictionary, okay? Which I hope everyone has used one in the past. All right, so tokenization, I have a word level tokenization, where every entry is a word, and I have at the other extreme character level tokenization. These are the 2 extremes. In a word level tokenization, things are pretty straightforward. However, there is a problem, as it's typically the case. The problem is that you may have a tokenizer and you may train your language model with the specific, let's say, tokenizer. And suddenly, someone is speaking to the Alexa speaker about neuroscience. And when they speak about neuroscience, guess what's happening? The unknown words are tagged as unknown. So when you have in a language model a lot of unknown tags as a sequences, things are not performing very well in the terms of prediction of the next token. So this is the main problem with Word, and people try to solve this problem, and they went to the other extreme temporarily, to the so-called character level tokenization, where now a token is just one character. And what is the problem there? Anyone can think about the problem where token is just a single character? Now the vocabulary is very, very small, right? It's trivially small, like 200 entries. Capital letters, small letters, numbers, whatever, symbol, whatever. Okay. However, if you use character level tokenization and you have the word hippopotamus, hippopotamus ends up being a very long sequence of tokens. What we have just learned when we have long sequences of tokens, we require significant, what we will be calling context memory, to store these tokens in order for us to make a prediction. We are dealing with long sequences. So that is obviously another extreme. And we arrived finally to some form of middle ground called subword tokenization. Out of many subword tokenizations, we will be dealing with a specific version called byte pair encoding. So byte pair encoding, or BP, is a tokenizer that has been used extensively in the GPT type of family of language models, and originates, as many things in this course, originates from the 60s, where people were in the habit of carrying floppy disks with them. So you want to do some computing, you carry the floppy disk. I was also one of these guys carrying floppy disk. Insert it, close the door, and then you press some buttons, and you could even hear the mechanics of the floppy disk being rotating and blah, blah, and so on. Something was coming on the screen 5 minutes later. Life was very slow back then. So the reason why we had to carry floppy disks is, despite many attempts, the storage was kind of expensive. I remember buying my first hard disk at the time. I'm not going to tell you the price and the capacity because you're going to laugh. Many people were in the business of trying to invent compression algorithms, like the compression. Many information theorists, the compression algorithms used today, like zip files, all this kind of strange extensions were invented at that era. So one of the compression kind of schemes at the time was called byte pair encoding. It's an encoder, and I'll describe the first principles of it here. So I'm going to describe effectively called byte pair encoding. So BPE. I should argue that last night I recognized that the page in the website where that the byte pair encoding is described is nowhere to be found. So I need to fix that during the weekend. I will post a chat message in your Discord to tell you that the page showed up again. And in that page, there was a very important web-based tokenizer. So I will treat tokenization into two parts. What I'm going to have in my notes right now, but I cannot use the page over here. During the review next week, I'm going to use the page and tell you something about the size of the tokenization versus several other things that I want to mention. Okay. So byte pair encoding. This was used in the GPT type of family of language models, and the premise is straightforward. Let me give you a very random, synthetically constructed example. Let's assume that this is the input text that I want to store, and I want to compress that storage as much as I can. So I'm going to be looking for other bytes, characters in other words, next to me, for example, that I can assign another symbol. So Z is the symbol. I'm using the assignments with capital letters to distinguish them. So the text now becomes Z, A, B, D, Z, A, B, A, C. Then another assignment, the text results into Z, Y, D, Z, Y, A, C. This is capital X, Z, Y. And then finally, with this last assignment, it's X, D, X, A, C. The premise of this encoding is that the storage needed for me to store this guy and this lookup table, it's smaller than the storage required to store this. Of course, in this trivial example, may not be happening, so don't make extrapolations out of this trivial example. But this was proven at the time that this is the case. I don't have any ranking on how this compression scheme results compares to others, either preceded it or obviously follow it. But I'm going to discuss what is happening inside the byte pair encoding in terms of implementation. Not a Python code here, because this Python is behind this tokenizer, which I don't have right now. But the sentence I want to use is yet another famous sentence. C sells by the share. Okay, so I'm going to use this example to see how the tokens are being created and how the vocabulary kind of evolves out of the byte pair encoding. So I'm going to start by suggesting that I am ranking all the symbols according to the frequency that they show up. So by dash, I mean the space symbol. Space symbol 5 times. The S symbol 5 times. The H symbol 3 times. Someone told me that there is a numerical error here, but don't read too much into it. Just try to understand the big picture here. So I have this first iteration, and I'm deciding to group together S and H, as each one of you must have figured it out by now that these are the 2 ones that are going to be merged first. So I'm assigning my symbol, capital Y is equal to SH. And in the second kind of iteration, the moment this assignment is actually happening, and this is the important thing, some of these symbols are going to be reduced in terms of frequency. The 5 became 2. Definitely, I am going to be adding the assignment with its frequency at the end of this column. And as you understand, as I'm progressing, some symbols will have frequency of 0, they will disappear. And some others will also show up. Like, for example, now that I have SH, let me also merge SH, but also use SHE. Now I'm using the previous symbol, which I have added in the second kind of iteration, and I'm combining it with a pair of SH and E. Right? So this is now a new symbol, and it will itself have a frequency. I'm going through this ranking and re-ranking all the time, and at some point, the moment I reach the number of tokens in this column to be equal to my vocabulary, desired vocabulary size, I stop the iteration. So this will be called V, capital V, for vocabulary. And I will very frequently refer to this symbol called the cardinality of the set V. The number of elements, in other words, of the set V. That is going to be my design vocabulary size. If I develop a language model for a smart speaker at home, that thing will be 10,000 entries, no more than 10,000 entries. If I define something for an LLM that I'm aspiring to deploy as a frontier model, that will be much, much larger. But depends on the application, you define your cardinality V, because this has some impact on the performance, which I'm highlighting in that page, which I cannot show you right now. But I will do that next year. So that's basically the back parent coding. And you will see an example over there in Python on how to implement that out of that tokenizer that I'm providing over there. Okay, which of course now brings us the following. That every single token now in my vocabulary has an index from 0 to cardinality V minus 1. Has an integer number next to it, right? So at the end of the day, the end result of the tokenizer is that I'll have my input text, I have a tokenizer, and I'm going to have a sequence of integer numbers coming out. Can I do anything with integer numbers? Well, obviously not. I cannot do much with integer numbers. What I need to have as input to my neural network is what? What every neural network needs in order to process anything. Vector. I need vectors. I need vectors to process anything in a neural network, right? From a dense all the way to the recurrent that we've done just now. I need vectors, or I need some multidimensional tensors like images, right? So I will then need to have capability now. I need to invest in the capability to take these integer numbers out of the tokenizer and convert it into vectors. And that conversion is very, very important. It's called an embedding device. I need to have an embedding device. So the sequence now is that I have some, I will call it pre-processing, which is the parsing stages that I had explained. I have some kind of a tokenization, and then I have another device called embedding device. This thing is going to give me the sequence of numbers, whatever. And this thing is going to give me the sequence of vectors. I hope you're following. This is going to give me a sequence of vectors, x1, x4, 151. These vectors, obviously, are not the x, they are the xt's. I was telling you a little bit in the current networks. Don't interpret the index here as the t index. It's the index of the vocabulary. This is the index of the vocabulary. I have 10,000 entries in my vocabulary. And if the tokenizer is x1, it gives me that this token was present to you in the input, then it's x551. This will be not the t index. So this is the first token. That's a second token, not the 551 token in terms of sequence index. That's what I'm trying to point out. So I'm going to have each of these vectors are going to belong to some dimensional space, D, I will call it. Yes, go ahead.
So for the word vocabulary, is that just all possible?
Yeah, like imagine now a word-based vocabulary is a whole dictionary from Aaron all the way to zebra.
And then for like the tokens to the embeddings, is that like 1-to-1? So like the same token? will
Yes.
give the same.
In the construction we are about to describe, it's called context-free construction, because we're going to see that we're going to need also contextual representations, right? That transformers will build for us. But right now we are not there yet. Every single token in my vocabulary will correspond to a unique vector, a dense vector, as it turns out, at the output of this embedding system. So I want to show you examples of desired embeddings and examples of undesired embeddings. Obviously, everyone here is able to tell us a trivial way where an integer number can be converted into a vector. If, for example, now I'm going to switch to word level tokenizers for us to understand. If, for example, I have the hotel, the token hotel, and the tokenizer gave it an integer number of 1,535. And if I have the token motel, and this gave it, 2010 or whatever, the integer number 2010. A trivial way to convert an integer number to a vector is to do one hot encoding. And the hotel, if we do that, we are going to result into x 1,535 to be equal to 0, 0, 0, 0, 0. Right at the index 1,531, I'm going to have a 1, and then followed by zeros. Do you agree that's the trivial way of doing this embedding? One for the encoding. If I do the same for the motel, you can imagine, I'm not going to write it, the vector of the motel will have all zeros except from a 1 in the 2010 location. The question I have is that if motel and hotel carry similar meanings, which is they do, what was the main operation we have been doing every time we are dealing with neural networks? We are doing dot products. We're doing dot products. So what I want from these representations in the d-dimensional space is for tokens that carry similar meaning to be close by in the d-dimensional space. That is the desired embedding that I want to construct. Because those tokens are going to result into, so effectively, the temporal, the language model, effectively, what we will do is we'll use the dot products which are present in every single equation, because when I write a matrix by vector multiplication, I hope you recognize I can write it as a summation of many dot products, right? So dot products are everywhere in the construction of language models and in the construction, in other words, of P models, because we are building statistical machines here. So let me show you an example of this construction. Just to have something visual in our minds. So over here we have a 10,000 entry vocabulary. And as it turns out, this is the word level vocabulary to make things simple to kind of understand. And we require D to be 200. Why 200? Out of the scope of the discussion we have right now. Could be 200, could be 768, could be anything, right? So this is the embedding dimension, the small letter D that I wrote earlier, right? And vectors start with 10,000 elements, one hot encoded, and end up with 200 dense elements, each one of them. That's the input and that's the output of that construction. However, each of these points here in this kind of point cloud is one word. Can we observe it in the 200 dimensional space? And obviously we cannot. The maximum number of dimensions we can observe with our eyes is 3 dimensions. That's why this thing is in 3 dimensions. Someone went and applied principal component analysis, like I was telling you a few moments ago, and went from 200 dimensions with a linear projection down to 3 just to visualize things. Having said that, the distances between the 200-dimensional vectors are still there, and we can calculate Euclidean distance between them, right? And I'm going to search for a word here that is called a car. And the nearest neighbors will reveal to me who is nearby the word car. Ranked according to the smaller to the largest distance. Driver is next to the word car. Cars, automobile, race, racing, vehicle, and things like that. So this is the construction we want to be able to achieve, right? This construction is going to be called word-to-vec, and it's going to, at the end of the day, be called contextual free representation. In other words, if you imagine that I have here the word bank instead of a car, whether the bank refers to the financial institution or the bank refers to the river, there's going to be only one point in this d-dimensional space. That is what distinguishes contextual free representations from contextual representations. In most instances, in other words, I'm going to be feeding into during the training of these embedding devices, the whole internet. The whole internet contains both Yahoo News as well as also National Geographic. So out of this kind of training exercise, only one point will exist as far as bank is concerned. Okay, so that's a limitation. We will evolve, however, into an architecture where depends on who is nearby, the context, that point changes depending on who is nearby. If nearby is money and accounts, that point will move closer to the meaning of a financial institution. If nearby is crocodiles, they will be moved closer to the bank, the meaning of the river, closer to the river bank meaning. Are you following what's going to happen? Okay, so we'll take one step at a time. And I'm going to start, although I'm not going to be able to finish it, that construction, this construction. All right, so let's see. Okay, so as I said, I am going to have as an input a one-hot encoded version of the word. I want to extract a dense vector representation of 200 elements long. And then this will be my encoder. And on the output, I'm going to get, how do I call it right now? I think I'm going to get it as, at the output, I am going to get a Z T. Okay, so the ZT is going to be D by 1, and WT is going to be cardinality set of V by 1. Okay, 10,000 by 1, 200 by 1. How I'm going to do this construction, though? I'm going to use a very important and very general approach in representation learning called pretext task-based learning, representation learning. What on earth is a pre-task? let me explain it this way. I will obtain the ZT by making a task which has nothing to do with a representation, building task, but has something to do with a prediction task. In this case, it will be a classification task. Out of solving a classification task, I will build the right representation. If my solution to the classification task is successful, I will claim that the representation building task is also successful. That is the definition of the approach that I will employ here. And I will go to get some intuition as to how this is done by, where's my, I don't have it. Oh, here it is. By looking at a guy called Firth, a famous linguist, who suggested the following. The word's meaning is given by words that frequently appear close by, which is basically what more or less we understand. I mean, if next to bank is like account and money, bank is going to be the financial institution. No matter, it's not going to refer to rivers. Unless we refer to rivers of money. Okay, so so basically, two keywords are there in this kind of sentence. Nearby, close by, which means points to some kind of a window around the bank. Frequently, which points to what? That's a question for you. And for 2 hours, I don't think I drank a single thing of water, and I'm going to have dehydration and die at some point. Yeah. The frequent, how do we interpret the frequent? Frequently. Well, it points to, remember, I was telling you something about probability, and we are counting events and divide by the number of events, right, to come up with a probability measure, right? Here, it points to a solution that is going to be, at the end of the day, probabilistic. Because I want to be counting, right? I'm going to be treating the tokens that are next to me, right, as probabilities. You know, how much, what is the probability that next to me will be the account? What is the probability next to me that will be money, and so on and so on. So I'll have a training kind of data set. The training data set is going to be trivial now. I'm going to have the construction of this kind of training data set. Let me tell you a little bit more about the training data set. Let's say I have text like Claude Monet painted the Grand Canal of Venice, blah blah, and so on. Obviously, for every single token, I have 2 tokens that precede it, let's say, and 2 tokens that follow it. For every single token, I have not shortage of training data. Give me any, you know, the whole Encyclopedia Britannica, so to speak, and I'm going to just have an infinite sort of training data that I can use in order to build this predictor. So the task that I was referring to is a prediction task of what could possibly be next to me if I am the World Bank. That is the pretext task. Okay. So now that we understand that there is ample of data to support, if you like, the task, let's see a little bit more formally what kind of probabilities I need to estimate, because we were in the business of estimating probability distributions from the very beginning of this course. And so we were estimating coming up with models that were estimating the probability of y given x, comma theta. That was or w was the column, right? So we were estimating conditional probabilities. So what is now the y and what is the x in this situation here? Anyone? We're trying to predict tokens that surround us. Therefore, the y is this guy. We are trying here to predict what the word that immediately is after us, after bank. given, remember the block diagram I just drew, the input is going to be the word bank. So the predictor I was referring to is going to have now a new form, not a new form, but is going to look a little bit different than I had. This predictor is going to be, I will call this to be called representation learner. It's going to have 4 arrows coming out. Y hat of t minus 2, y hat of t minus 1, y hat of t plus 1, and y hat of t plus 2. These are the conditional probabilities that I'm familiar with of 2 words behind me, 1 word behind me, one of a word that follows, and 2 words that follow. This is basically the window. If the window is -2 to +2, these are the predictions that I'm interested in. There's no Z coming out. The Z is going to be built inside this representation learner. So we'll see that next time, how this representation learner is going to be built. What is the architecture of the P module, in other words? We will start from basics of maximum likelihood estimation and build it from first principles to understand how MLE will help us extract out the ZT out of it. All right, thank you. Where is my attendance thing? Wait, I need to disappear.
I didn't get a chance to sign in.
Yes,
I didn't get a chance to sign in. Is that what?
over there,
Oh,
the crowd.
Thank you. I'm sorry.
Oh. The weight of the midterm is 20%.
Right, it's like that. Are you gonna release the midterm stats?
That I don't typically don't, because there's no reason to release them.
And it would be nice to know like how we did.
Relative to the others.
Yeah.
Oh, okay. Yeah, I can release them then. Okay.
Or do you just like know the average?
I have no idea. No idea. In fact, I just found the grades they told me.